Section 4.4, Part 3. Well, if the fundamental theorem of calculus was an amazing discovery, it's exciting to find the area under a curve using integration techniques and then plugging in the top number and the bottom number and subtracting them. That's huge. But the second fundamental theorem of calculus, not as impressive. If f is continuous, which f has to be continuous to even integrate, okay? We may not have made that clear before, but f has to be continuous to integrate at all. So from whatever your limits are, here to here, the function has to be continuous in that interval in order to use the first fundamental theorem of calculus. But the second fundamental theorem of calculus goes along with that. If f is continuous on an interval containing on an interval, open interval I, containing a, so a is this number. It has to be a number down here, or else we'll have to change a few things. Then for every x in the interval, the derivative of the integral of a function equals that function. Ooh, a derivative of an antiderivative? They undo each other? Ooh, that's not really that big of a deal, is it? We kind of knew that, right? Like if you multiply by something and then divide by the same thing, you're left with the original thing. Well, it's not exactly the original thing. If you take the derivative with respect to x of an integral with respect to t that goes from a constant to x, then it will just equal the function with x in it. So the derivative of the integral of a function equals that function with this top x value plugged in, as long as this denominator is a constant. Okay, so let's see how that works. Integrate to find f as a function of x and demonstrate the second fundamental theorem of calculus by differentiating the result. So we're going to integrate this, and then we're going to do the derivative of it and show that the derivative of the integral will just equal this function with x in it. Ooh. So we're going to show that f prime of x, so the derivative of this and the derivative of this will just equal the fourth root of, oops, not t, of x. All right? That's the second fundamental theorem of calculus here that we're demonstrating. All right, so let's integrate this. So first, before we integrate, so I'm going to keep that integral sign there because I haven't integrated yet. I'm going to write t to the 1/4 dt. And now I'm going to integrate, and it's a definite integral because it has limits on it. So you add 1 to the exponent, so that becomes 5/4. Divide by the new exponent, and dividing by 5/4 is the same as multiplying by 4/5. And then we're going to put our limits of integration on there and actually put x in, excuse me, so that becomes that, not that. And then plug the 1 in. And subtract the 2. 1 to the 5/4. You can either do 1 to the 5th first or the 4th root of 1 first. Both of them are 1, and then do the other, it's still 1. So we have 4/5 here. So we have 4x to the 5/4 over 5 minus 1. That is what f of x equals. So we integrated to find f as a function of x. So here's capital F as a function of x, so it has an x in it now. And demonstrate the second fundamental theorem of calculus. So we're going to show this by differentiating the result. So we're going to actually take the derivative of this f that we found. So what's the derivative of 4/5 x to the 5/4? You take your exponent out in front, multiply it out in front, and subtract 1 from the exponent. So 5/4 minus 4/4 is 1/4. And the derivative of, well, why did I write a 1 there? I meant 4/5, sorry. 4/5 times 1 is 4/5, not 1. The derivative of 4/5 now is 0. Those two cancel, and all we're left with is x to the 1/4, which is the same thing as the 4th root of x. Hey, that's what we were supposed to show. Ooh, big deal, right? Well, For one thing, sometimes we can't actually evaluate this integral. So it helps to know that the derivative of a function and the derivative of the integral is just equal to this function with x plugged into it. Because sometimes we can't actually go through this step of integrating it and getting a value that we could take the derivative of to show it. So that's one thing. So here's an example of that. We can't really integrate this yet. We don't have a quotient rule, and it's going to take us quite a few chapters to get to the point where we could integrate this. And I hope you can figure out that there might be even some functions that in Calc 1 you wouldn't be able to know how to integrate. And some functions you can't even integrate without the aid of a computer. So that's the partial reason for having the second fundamental theorem of calculus. If we want to find f prime of x, we're going to do the derivative of both sides. So the derivative of the integral from 1 to x of t squared over t squared plus 1 dt. So the derivative of the integral cancel each other out. As long as this is a constant down here and we just have a function x here, we can plug x in. So that would equal x squared over x squared plus 1. Okay? Well, this is an extension of the second fundamental theorem of calculus, which they will use a lot on the AP test. Not a lot, but this is the form of it that they would use more than the first form. If you're taking the derivative of an integral of a function from a constant to not just x, but that stands for a whole function, so anything other than x, more complicated than x. So like x squared or 2x or x squared plus 5x minus 7, anything other than just plain old x. Then the derivative of the integral of that function from a to a function is that function plugged in, that this u plugged into the outside function, times the derivative of that function. So times the derivative of this thing here. All right. So get your thoughts around that. The derivative of the integral is this function, this regular function with this plugged in, just like in the second fundamental theorem of calculus we've been talking about so far. So we just plug that in, but also times the derivative of that upper function. Now, how does that fit with what we just talked about here? Well, if you multiply, you plug that x in, so we got that x plugged in, and then you multiply times the derivative of x. What's the derivative of x? That's just 1, right? So really you're just multiplying by 1. So that's why we didn't bring it up then. But that's actually, this is actually still the second fundamental theorem of calculus, just with a more complicated upper bound. So let's do an example of this. If I want the derivative of this integral, so the derivative of the integral from 2 to x squared of 1 over t squared dt. So we're trying to find the derivative of both sides. The derivative of the integral, they pretty much cancel each other out, right? You plug that in there. So instead of t squared, we're going to have x squared squared, but then times the derivative of that x squared. So the derivative of x squared, or x squared prime. So it's 1 over x to the 4th. You multiply exponents here. And the derivative of x squared is 2x. So that becomes 2x over x to the 4th, which is 2 over x to the 3rd. So whenever you have anything as your upper limit other than plain old x, then you've got to multiply by the derivative of that other than x. All right, the net change theorem. This is my mantra. It's going to be called integrate the rate, integrate the rate. I'm going to say it many times. It comes up a lot on the AP test. A lot of word problems involve integrating the rate. Now, why would we do that? The net change theorem. The definite integral of the rate of change of a quantity, f prime of x, gives the total change, or the net change in that quantity. So if I want the net change of the rate that the water is flowing into a pool, you integrate the rate to get how much total water has flowed into that pool. Or if I want the net amount of change of the sand, so I know the rate that the sand is falling onto a pile from a conveyor belt. If I want to know the total amount of sand that is now on the pile, integrate the rate, and that gives you the total net change. If I know the rate that the temperature is changing, and I want to know the total temperature change, integrate the rate that the temperature is changing. All right. Here's an example. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. T is between 0 and 60. So that's time. Minutes. Find the amount of the chemical that flows to the tank during the first 20 minutes. So, integrate the rate is my mantra, right? If I want the amount of the chemical that flows into the tank, I'm going to integrate the rate that it's flowing into the tank with respect to time. For how long? During the first 20 minutes. So that 0 to 20 minutes are my limits of integration. So integrate first before we plug in any numbers. Antiderivative of 180 is 180t. Antiderivative of 3t is 3t squared over 2. Integrate that from 0 to 20. Plug in your 20 in both places. And then you plug in your 0. Well, you can probably tell that's just going to be 0. So this whole thing is 0. So calculate that. And we've got 4,200. Always remember units. If our rate of change was liters per minute and we're integrating, it's like we're multiplying, undividing by per minute. So now we're just back to liters. Another example of the net change theorem, the velocity of a particle moving along a straight line. S of t represents the position at time t, and v of t is the velocity. If we want to find its displacement or its net change in position, so if it started here and went back and forth and back and forth and back and forth and ended up here, I want the net change from here to here. So that's what we're going for, the net change. It's given by this. We integrate the rate, integrate its speed, but velocity is speed with direction, right? So we're going to integrate the velocity, plug in. When you integrate velocity, you get the position function, and you plug in your b and your a, and you subtract them. That will give you your total displacement. So for example, if we have a particle moving along a line so that this is the velocity, it's that many feet per second at time t. Find the displacement of the particle from time t to 5 seconds. So wherever it started, I want to know how far away it ended up. I don't care if it went forward and backward and whatever, up or down, whatever. How far away is it from where it started? That's what displacement is. You integrate the rate. All right, so we're going to integrate t cubed minus 10t squared plus 29t minus 20 to give you the position. And we're going from 1 to 5 seconds. Notice these limits of integration always relate to this variable, t, the variable that's in the integrand. So antiderivative of t to the third is t to the fourth over 4 minus 10t cubed over 3 plus 29t squared over 2 minus 20t from 1 to 5. Plug in your 5 and then you plug in your 1 and you subtract the two of them. When you plug in the 5, you get 25 twelfths. When you plug in the 1, you get negative 103 twelfths. Subtracting the 2, you get 128 twelfths, which reduces to 32 thirds. And the units on that, since it was feet per second, we're basically getting rid of the seconds, multiplying by seconds. So we get feet, 32 thirds feet. We're going to continue this in video number 2.